Functional programming is hot right now. Python is hot right now. A functional programming course in Python is perhaps the greatest mashup since avocado toast met Instagram. Functional programming, like object-oriented programming, is just a style for writing code. Before starting Boot Dev, I was working as a hiring manager on a team of Go developers. And it always frustrated me when a developer on my team didn't really understand the differences and the similarities between the two patterns. Look, you can prefer functional programming, you can prefer OOP, but it's really important to at least have an understanding of both. And no matter what your programming language is, it's really important to at least understand the core ideas of functional programming because they apply everywhere. So what's in this course? Well, we'll go over functional programming basics like declarative code and immutable values. We'll cover first-class and higher-order functions, pure functions, recursion, function transformations, closures, currying, Python decorators, and sum types. Now, if you get nothing else out of this course, I hope you at least walk away with the ability to use recursion without breaking out in a cold sweat in the coding interview. Now, to address the elephant in the room, why Python? Well, truth be told, Python is the language that most boot dev students are already familiar with, and frankly, a lot of developers out there are already familiar with. Is Python a purely functional language? Not even close. But that's okay. We can still learn the most important functional concepts, again, that are applicable in all languages, even Python. And those concepts are going to be useful all over in the industry. Again, regardless of whatever programming language you use at work. So who's teaching this thing? Well, not me. I'm Lane, the founder of Boot.dev, a platform for learning backend development online. I've been building software for about 10 years. I was a hiring manager for about 3 of those before going full-time on Boot Dev just a couple of years ago. Now, I wrote this course and a few of the animated explainer videos that we'll pepper in later, but Travi, or Tech Savvy Travi, as he's better known on Twitter and Twitch, is going to be your guide through it. See, a couple months ago, I was staying at an Airbnb in Montana to attend Big Sky DevCon, and I was hanging out with Travi, Warren, and the Primogen, and Travi would not shut up about how he was teaching himself lambda calculus. And after listening to him rave about arguably one of the most stale subjects of our time, I just knew he'd be a really good fit for making a walkthrough for this course. Now we gotta talk about something. Please do not binge watch this course from start to finish. The best way to take this course is to do each lesson on your own first, and then just watch Travi do it afterwards, partly so that if you can get stuck, he can get you unstuck, but also just so that, he can give you a deeper understanding of the material after you've already had a chance to challenge yourself. You can always bookmark individual timestamps in this video, so don't feel like you need to do it all in one sitting. And just so you know, this course is actually just one part of a full backend developer learning path over on boot.dev. So if you're interested in going from zero to hireable as a developer in Python or Go check that out. Now, everything you need for this course is available for free here on YouTube, and the lesson text is actually also available for free over on boot.dev. And I'll drop a link to that down below if you want to follow along there. It's free to make an account on Boot Dev, and all of the content is also available for free. A paid membership, which again is totally optional, just unlocks all of the interactive features on Boot Dev. Things like quests, achievements, progress tracking, Boots, our AI mentor, solution viewing, and a certificate when you complete the course. So if you do end up enjoying the demo and like the interactive features, you can use Travis's code TRAVI for 25% off your first payment. That'll directly support him, and again, completely optional. You can still take this whole course for free without it. Now, if you get stuck or have any feedback on the course, the best place is the boot.dev Discord community. We have an incredible group of talented developers that just like to hang out and help each other, so definitely check that out if you're interested. Again, link is down in the description below. Okay, with that, let's talk about functional programming.
Good afternoon, or morning, or evening, wherever you're at. I'm Tech Savvy Travi, and today we'll be learning functional programming. There's a twist. We'll be learning it in Python. Yes, Python. So let's get into it. So what is functional programming?
Functional programming is a style of programming that you use if you like keeping your code simple, writing fewer bugs, and flexing on OOP devs by saying things like referential transparency and the lambda calculus. A lot of people assume that functional and object-oriented programming styles are opposites, but really, they're just different. Imperative programming is actually a better opposite to functional programming, which, to be fair, object-oriented programming takes no issue with. Take a look at this imperative code. First, we create a new car. Then we call the car's add gas method and add 10 gallons of gas. Then we call the clean windows method, and then we set the four-wheel drive property to true. This code executes in order, one line after another. At every step, the car variable is updated. So to debug this program, we need to think about time. The car has 0 gallons of gas on line 1, but by line 3, the same variable has 10 gallons. A more functional approach would look something like this. Instead of changing the value of the car variable, we write functions that accept a car and return a new copy of the car with updated values. The big difference is that the functional example is declarative rather than imperative. The entire program is a single expression, and it doesn't require us to continuously re-update the same car variable. Now, it might feel like a trivial difference, but by never mutating the state of a variable, and by using nicely encapsulated functions, our code is actually easier to test, to debug, and to think about. Functional programming is just another style of writing code. It tends to be more popular in academic circles, but some of the more practical and useful concepts that have come out of the functional programming paradigm have found a home in mainstream software development.
If you have procedural programming that declares what and how to do something, very important how you're doing it, then functional programming is more declarative, which means you tell it what you want without focusing on the how. So we have some examples here of imperative and then functional code. I think the overarching theme is we're working on this doc-to-doc tool, like pandoc. So for this first one, pretty easy. It says use the provided functions, center title and add border. Center the title before adding the border. Do not create any variables and use only one line of code in the function body. I do want to say that functional programming isn't really about not creating variables or, trying to quote unquote code golf where you use only, as few characters or a few lines of code as possible. But for the sake of this, we will follow the instructions. So if we want to center the title first, we do center title document, and then we need to wrap that in the add border function so that the result of center title gets passed to add border. We can submit that and we're good. First lesson done. So this will be good. Why Python? Frankly, Python is not the best language for functional programming. You don't say. So it doesn't have static typing, everything's mutable, no tail call optimization, side effects common all over the place. It's got imperative and OOP styles. Purity is not enforced, and some types are hard to define. Pattern matching is weak at best. So seriously, why are we using Python? So the reason is you already know Python. You've been using Python in the courses so far leading up to this point. So the concepts can still be taught as long as you understand the limitations. And they do plan to release functional programming 2 with something like Haskell, OCaml, or Elixir. Nice. So why learn functional programming in Python? Is it because we already know Python? Because values are immutable in Python? Because it's statically typed? Or because it has great support for pattern matching? That's because we already know Python. Easy peasy, on to the next one. In FP, we strive to make data immutable. Once a value is created, it cannot be changed. Immutable data, on the other hand, can be changed after it's created. So why do we care? Because immutable data is easier to think about and work with. Yes, very much so. So if a variable is immutable, you can be sure that it hasn't changed since it was created. That is the source of a ton of bugs, is mutable variables. And in Python, you have tuples and lists. Tuples are immutable and lists are mutable. So you can append to a list, but you cannot append to a tuple. That's pretty important. So you can create a new copy of a tuple using values from an existing one, but you can't change the existing tuple. This just goes over that. So the assignment here is to add prefix function accepts 2 arguments, a document and documents, a string and a current tuple of strings. So we want to add a prefix of x, where x is the next index in the tuple. First document should be 0, the next should be 1, etc. Then we return the documents tuple with the new document added to the end. So this one's a fix the bug problem. If we try to run this, we can see 0 pass 1 failed. So the tuple object has no attribute append. That makes sense because It's not mutable. Tuple is immutable. So we have the new doc, and what we have to do is we can append the new doc tuple to the documents tuple. So we have new doc, and then we're going to say documents equals documents plus, and then to create a single value tuple, we can do parens and then new doc, and then we have to, this is very important in Python, you have to put a comma, and then you can return documents. Now if we submit, good to go. On to the next one. Declarative programming. Functional programming aims to be declarative. So again, we want to know what, not the how. And this is comparing it to CSS, which is declarative. And I think I just answered the question. Whoops. So it doesn't execute line by line. It just declares the style, and that's what you get. You don't need to know how it does it. You just need to know that it does it. This would be using tkinter, shows you how an imperative style would do it. You have tkinter, you have the master, you're setting geometry, you're changing, you're mutating state. All right. CSS is typically imperative or declarative. It is declarative because it says what you want and not how to get it. A script that does one thing after another is imperative. That's telling you how it's happening in step-by-step fashion. It's math. Functional programming tends to be popular amongst developers with a strong mathematical background. After all, a math equation isn't procedural, it's declarative. Take the following math equation. So the E looking thing is just the Greek letter sigma, and it represents the sum of a collection. X is the collection of numbers we're averaging, and N is the number of elements in the collection. Average is equal to the sum of all numbers in collection X divided by the number of elements in collection X. All right, let's actually read this. It's very important to read the assignment. In the world of document conversion, we sometimes need to handle fonts and font sizes. Complete the getMedian font size function. Given a list of numbers representing font sizes, return the median of the list. So this would be 2, and this would be 7. Second list is out of order. Order the list, then find the middle index and return the middle number. If there's an even amount of numbers, return the smaller of the two middle numbers. Okay, so 7 and 8 would be the two middle numbers, and we're taking 7 because it's the smaller one. I know it's not a true median. Okay. Just return none if the list is empty, and then we have some helpers here. Your code for this lesson should not use loops or mutate any variables. It's okay to create new ones. Yeah, like I said before, it is okay to create new variables. So first thing we can do is we can check if the length of font sizes is 0, because we know if the length of font sizes is 0, then we are going to return none. So we're going to return sorted, and we're going to take font sizes, and we're going to get the index of the length of font sizes, and that's going to be -1. So we're going to use floor division. So we've sorted our font sizes, and then we're getting the index of the length of font sizes -1, and then we're using floor division to get the middle of that. And doing the length -1 will get us the smaller of the numbers, if there's 2, if it's even. So we can submit that, and we're good to go. Classes versus functions. It says they run into developers, they learn about classes, they want to use them everywhere. They learn functions first, and they think they're inferior. When in reality, it is classes that are inferior. No, but classes are great if you need state, and if you want to encapsulate something that needs to share state between different methods, it's great for that. But they do get overused, in my opinion. If you're unsure, default to functions. So if you need something long-lived and stateful, that's the key here. Then you reach for classes. And this says that classes encourage you to think about the world as a hierarchical collection of objects. Objects bundle behavior, data, and state together in a way that draws boundaries between instances of things like chess pieces on a board. Okay. And then functions encourage you to think about the world as a series of data transformations. Functions take data as input and return a transformed output. For example, a function might take the entire state of a chessboard and a move as inputs and then return the new state. Use what feels right to you in your projects and adjust and refactor as you improve your skills. I wouldn't say just use what feels right, but I would say go for functions, see how far they can take you, And if you find yourself passing around this state all over the place between the same functions, you can always encapsulate it. So I would say lean towards function first. Then if you need it, use a class. And little hint, you probably won't need them as much as you think. Which is better? Functions, classes, obviously function. No, they're good in their own special ways. On to the next one. Which encourages you to break down problems into instances of stateful things. That is classes. That's right, classes. Next one. So this one's about debugging. Debugging. So it's nearly impossible, even for tenured senior developers. That's me, by the way. That's why to write perfect code the first time. That's why debugging is such an important skill. Trouble is sometimes you have those elegant one-liners that are tricky to debug. If the output of get player position is incorrect, it's hard to know what's going on inside that black box. Break it up. Okay. Then you can inspect them individually. Yes. Again, why you don't really want those nice little, seemingly nice little one-liners going on. Then once you've run it, found the issue, solved it, you can remove the print statements. All right, let's, so we got format line. We got fix the format line function. We're going to fix it, and we're going to apply the following transformations in order. We're going to strip white space from the beginning and end of the line. And then we're going to capitalize every character in the line. And then we're going to remove any periods from the line. And then we're going to suffix the line with an ellipsis. That's only 3 dots. We got 4 dots here. We immediately know that's wrong. All right, so we're going to break this up to figure out what is going on here. Okay, we can just start breaking it up, right? Call this result. Okay, and then so we already know that if we run this, it's going to fail. But now we can print the results, see what it looks like before that. So this is saying we expected to capitalize everything, but it's actually capitalizing just that first letter. We'll just we'll break it all down. We'll call this stripped, okay, and then no semicolons in this one, and then capitalized or upper, and then so this will be stripped dot capitalized, and this will be upper dot replace. And we'll call that one no periods, and then we're going to print the result. And really, you don't even need to do all of that. You don't need to figure out what to name them. You can just name them one thing. Doesn't matter really. And then we're going to go upper, prefix that spelling real quick, no periods, and then no periods. And then we can say with ellipses, like that, and return with ellipses. And then we can print with ellipses. We're just going to go with full bore and print all of them, right? See where it's at every step of the way. Okay, so you have the input. You can't spell America without Erica. The tip right here is to sometimes add a character. Yeah, be careful about white space, because right here in the console, we can't really see what's going on with the white space. So what we can do is we can do an F string, put that there, and then we can add little pipes right there to it. So you can see, oh, we have input, friend and crazy. And so we're actually stripping our strip, but we want to strip all the white space. So we'll just call strip. And now we can see right there, we're good to go. And for the rest of them, we don't really need that white space sensitivity kind of thing. We can verify that there. And we can say upper. So it appears that we don't have them all capitalized. We just have the first letter of every string capitalized. And that's because we want uppercase. As you can see, upper capitalizes an entire string. Capitalized capitalizes the first letter. It's not uppercase, it's just upper. By the way, I am not a full-time Python developer. This is it's not important to, I think it's important to note that, it's not near as important to know the ins and outs of a language, which can be great. It can make you really fast, very comfortable in the language if you know the standard library and all that. But it's much more important to know what you want, know the concepts and what you want as the outcome. That way, you can always look up the ins and outs of a specific language. We strip the white space. Yep. And we have now gotten into upper. But we can see here, uh-oh, it's still got period at the end. So we need to get rid of that. It's because we're actually doing a comma and we want a period, right? And then very easy to see here, we're not adding an ellipsis, we're adding 4 dots at the end instead of 3. Boom, passed all together, good. Once you're done with that, you can go ahead and remove all those excess print statements. You don't want to leave debug code in your final result. We wouldn't want to do that, would we? And we can submit. And that is another one down. Functional versus OOP. Functional programming and object-oriented programming are styles. One isn't inherently superior. Yeah. We went over this. We know they're not always at odds with each other, though. They're not opposites. Of the 4 pillars, inheritance is the only one that doesn't fit with functional programming. And some argue that inheritance isn't actually part of. It's not really what makes something OOP. So they're basically the same. It's not true, but the immutability and stateful instances is really the biggest difference there. And inheritance isn't seen at all because you would need mutable classes. Encapsulation, polymorphism, and abstraction are still used all the time. Yep. And when working in a language that supports ideas from both, like Python, JavaScript, or Go, the best developers are the ones who can use the best ideas from both paradigms effectively and appropriately. Functional and OOP programming are all about writing faster code, writing code that uses less memory, writing code that runs on any machine, or writing cleaner code. I don't like cleaner code. I don't love that. But I get what they're saying. It lets you write concise, declarative code, and it's easier to debug. It's easier to abstract further if you need to. And it is why we write functional programming. Functional code, amongst other reasons, but this is the answer, unfortunately. So OOP's concept of blank conflicts with functional programming, and that is going to be polymorphism, inheritance, encapsulation, or abstraction. And functional programming has all of these except inheritance. Easy peasy. That is the end of chapter 1. Functions as values. In Python, functions are just values, like strings, integers, or objects. For example, we can assign an existing function to a variable. Yep. So this assignment is, with the popularity of generative AI, like ChatGPT, we need to be able to convert files into pure text to be injected into prompts. Complete the file to prompt function. It should take a file dictionary and a toString function as inputs and return a formatted string. The provided toString function is responsible for converting the file dictionary into a string. You don't need to implement it. It's a value passed to your function. However, your function should wrap the result of toString function in triple backticks to format it as a code block. So, for example, we have an example string. There are a couple ways to do this one, but the key here is that in functional programming, and even in Python has this too, you can define a function and then you can pass that function as a value to another function, and you can assign it to a variable. You can do a lot of things with it. So if we do a string and then we say, let's call this file string, and then we say toString file, and then we can return, we need to do an F string, and we can do triple backticks, and then we need a new line. We can put file string there, and then backticks. Oh, we need a new line there, and we should be good to go. Boom. So the key there is that we're getting the toString function passed as a value to our function. Very cool. Anonymous functions. An anonymous function has no name, and in Python, they're called lambda functions after lambda calculus. I think he means the lambda calculus, but that's okay. Here's a lambda function that takes a single argument x and returns the result of x plus 1. Notice that the expression is returned automatically. No need for a return statement. We need to complete the file type getter function. It accepts a list of tuples where each tuple contains a file type and a list of associated file extensions. So it wants us to create a dictionary that maps each file extension to its corresponding file type. And we could do this, we really could do this with a nice dictionary comprehension, but that wouldn't be functional. It's a nice, concise syntax comprehensions are in Python, but they are imperative actually. So we're going to return a lambda function that accepts a string and returns the corresponding file type. If the extension is not found in the dictionary, the lambda function will return unknown. It says I use the .get dictionary. I guess I here is Lane. Lane personally speaking to us. And so what we can do is we can say, we make a new dictionary, and then we have a list of tuples. So we can say for tuple in file extension tuples, then we can say for extension, this is not better. This is not, dictionary convention would be just fine. So we can do the first index of 1 will have the associated file extensions, okay? And then we're going to do our D index of extension is going to equal T index of 0. Always name your always name your variables well. This is not good. So this is like going to be file extension dictionary. Okay. And then we call this, we can actually do this. We can go file type and extensions. There we go. So then we can do extensions and we can do file type. Okay. And what we're going to return is a lambda. So we're going to say return a lambda that takes an extension, and it's going to return the file extension dict get the extension, and then we can get takes a fallback value, and that's going to be unknown. We can run that, passed, good to go, first try, submit it, boom. So moving on. First class and higher order functions. A programming language supports first class functions when functions are treated like any other variable. That means functions can be passed as arguments to other functions, can be returned by other functions, and can be assigned to variables. So a first class function is a function that is treated like any other value. A higher order function is a function that accepts another function as an argument or returns a function. Python supports both of those things. So you can assign f to square after you define square, and you can have my map here, which takes a function, an argument list, and then you can pass this function square as a value to it, like we did in the first lesson of this, and use that function inside of the function definition there. So what is a function that returns another function? That is a pure function, a higher order function, a first class function, or is it based? It is super based, but it's a higher order function. Which is the higher order function in the second example? Let's go down to the second example. Is it square, mymap, or def? Well, it's not def. So mymap takes a function, and we know that is what a higher order function is. So it is mymap. Woo! Whoa, I'm getting all sorts of things. Okay, map, filter, and reduce are 3 commonly used higher order functions in functional programming. In Python, the built-in map function takes a function and an iterable as inputs. It applies the function to each element in the iterable and returns a new iterable with all the results. I believe it actually turns a type of map, but regardless, with map, we can operate on lists without using loops and nasty stateful variables. So if we have square, we have nums, which is a list. We can say squared nums equals map square to nums, and then we can print a list of squared nums. The list type constructor converts the map object back into a standard list. So for this assignment, Markdown supports 2 different styles of bullet points, the dash and the asterisk. We prefer the asterisk, so we need a function to convert any dash bullet points to asterisks. So we're going to complete that function. The return string should have any lines that start with a dash replaced with an asterisk. Easy peasy. So we have this becomes that. The dashes get replaced with asterisks. We'll use the built-in map function to apply the provided convert line function, okay, to each line of the input string. We can use split and join to split the document into a list of lines, then join the lines back together. For this one, we need to split the lines by a new line. We'll call this lines equals document.split, and we're going to split by the new line, right? And then we can say mapped equals, we use the map function. We can map our convert line, and we use it on the lines, and then we'll call this joined, and that's going to be, and we can use the new line character dot join, and we're going to join mapped, and then we can just return joined, and we should be done. So we split the lines, we map over them, we join them. If we wanted to, and again, this is not the point of functional programming, is to do this, but these can obviously be combined into something a little more, well, some might consider a little more elegant. I don't always agree with that. I think creating variables is just fine. It often makes it easier to debug, but we can just do it like that. So we can see we split the lines, we pass that into the map function. We use the convert line function, which is defined down here, to map over each line, and then we join it all back together. And we can run that, and we're good. Chapter 2, Lesson 6. Filter. The built-in filter function takes a function and an iterable, in this case a list, and returns a new iterable. Yep, that only contains the elements where the result of the function on that item returned true. Okay, so in this case, we're filtering out anything that is not even. So it only keeps one. It's only going to keep ones that return true. So it'll only keep the even numbers here. All right, for this assignment, we need to complete the remove invalid lines function. It accepts a document as input. It should use the built-in filter function and a lambda to return a copy of the input document, but remove any lines that start with the dash character. Keep all other lines and preserve trailing new lines. So this should become this, without the line that starts with a dash. Then we can use join, and we have a starts with. String.starts with is pretty self-explanatory, and then we have split again. So for this one, what we can do is we can say filtered equals filter by lambda, and we're going to say for each line, we're going to say that it's got a not starts with, or not line dot starts with a dash. And then again, kind of like the last one, we're going to go document dot split n. That's going to get a split on the new line. Let's make this a little wider here. And then we can go down here. We can return new line character dot join filtered. Right? I want to split that one up too. I just don't like the lines being that long. So we just go lines equal document dot split there, and should be good to go. And we are. First class functions, reduce, chapter 2, lesson 7, reduce. The built-in functools.reduce function takes a function and a list of values and applies the function to each value in the list, accumulating a single result as it goes. So if we reduce and we have concatenate, and we have a list of words, we just keep, this will just keep swimming. It's important to know that with a reduce function, you have an accumulator, and then you have your current object, the current iteration of the object, and then some people call it the previous or the accumulator, which you use to build up a result, basically. This requires us to import functools. We can do that, or we can say we can do it how it is. We can say import functools, or we can say from functools import reduce, if we just want that one, right? We don't need all of them. I don't care about bin mode. So this is our assignment. We're going to complete the join and join first sentences function. Join is a helper function we'll use in join first sentences. It takes two inputs, a doc so far accumulator string. It's similar to the sum so far variable in the above example. And then it has a sentence string. This is the next string that we want to add to the accumulator. Okay, so it returns the result of concatenating the doc and sentence strings together with a period and a space between. So we have, this is the first sentence, this is the second sentence, and then this is the first sentence, period, space, this is the second sentence. And then we have join first sentences, which accepts two arguments, a list of sentence strings, and an integer n. This is where we're going to use reduce alongside join to return a single string, the result of joining the first n sequence sentences in the list. And it should also add a final period, but no trailing space to the end. If n is 0, just return an empty string. So we can do that first right here. We can just say if n equals 0, then we return empty string. Take care of that, edge case first. So we can use list slicing to get the first n sentences. Okay, there's a syntax for that. It's the colon and another number of items you want from that list. And here's an example of the expected behavior. This is the first sentence. This is the second sentence. This is the third sentence. And we only have 2 passed in. So we only get the first and second joined by a period and a space, and then also ending with a period, no spaces. Alrighty. This one is a little bit more challenging, but I think that will be just fine. We can quickly knock out our join one. We know that we want this to be the doc so far, and then we're gonna need to return it. And then we're going to append. You can just use the plus operator to append a string. And we get a period and a space, and then the sentence. That's going to be that. Okay, so we know if it's n, we return an empty string. And then what we're going to do now is we're going to return the result of reducing, and we're going to use the join function as our function that we're reducing with. And then you can see we have the doc so far. That's our accumulator. And we're going to want the number of sentences just up to n, right? And then we can run. Oh, see, minor detail, but we need to, we always want to pay attention to the minor details. And we're going to want to add that trailing period. And we're good to go. Just like that. That wasn't so hard. Reduce is a little bit more complicated than some of the other ones, and a lot of people forget how to use it, but it's very powerful. And if you think about it like a for loop, I think it makes a little bit more sense, right? That's chapter 2, lesson 7 finished, and we're on to the next one. So reviewing map, filter, and reduce. Map, filter, and reduce really kind of, if a language starts to adopt functional paradigms, that's where they start. You'll see map, filter, and reduce in a lot of languages, even ones that are mostly imperative or mostly procedural. So if you take a look at this imperative code, it calculates the factorial. Here's the same one using reduce. Okay. Yeah, you can just see how much, I don't know if this is the best case, but okay. In the functional example, we're just combining functions to get the result we want. There's no need to reassign variables, and the loop is inherently stateful. Yeah, you have an accumulator, and then you're reassigning to that accumulator. In this case, multiply using the multiplication assignment operator. So, which is an imperative way to apply changes to a list of items. It is a loop or a function. That is a loop. Well, what is the primary advantage of composing functions instead of using loops? TJ will finally be proud of you. Performance, composing functions is faster than loops, or avoiding stateful mutations, which can be harder to debug and reason about. I do want TJ to be proud of me, but it is avoiding stateful mutations. All right, we're done with chapter 2. Chapter 3, lesson 1.
Pure functions are almost always a good idea, just like using tabs for indentation. And pure functions have 2 properties that make them pure. They always return the same values, given the same arguments, and they cause no side effects. Let's look at the first point. Here's an example. We have an add function that takes a and b as input and returns the sum. Now, no matter how many times you call add with the same arguments, you'll get the same result. I'll add with 2 and 3 1 trillion times in a loop, and you'll go crazy waiting for anything but 5 as the result. Now let's take a look at a similar but impure example. First, we'll declare a global variable called result and set it equal to 0. Next, we'll define a function called add2result. Now this one only takes 1 input, we'll call it a. The first thing it does is declare that the result value, or I should say the result variable, is a global variable. In Python, this is required just so that we're allowed to access that global variable from within a function. Next, we'll add a to the result and return that sum. Now, the interesting thing about this function is that every time you call it, even with different inputs, you could potentially get a different result. For example, the first time I call add2result with, say, the number 5, I expect to get back 5 because we're going to add 0 to 5 and return it. But if I call add2result again with the input 5, I won't get 5, and that's what makes it impure. Because the result variable now has 5 in it already, we'll be adding 5 to 5 and we'll get back 10. And this is why pure functions are so convenient to use in the majority of cases. Every time you call them with the same inputs, you expect the same outputs. You don't have to worry about there being hidden random number generators, the state of a database, or whether or not an internet connection is available in order for the function to work as expected. And because they're predictable, they're easy to test and debug. You can write an entire suite of unit tests for a pure function, and assuming they pass, you can expect, not just expect, but they will work the same way in production given the same inputs. If you've ever experienced the "well, it works on my machine" meme, that's not a problem with pure functions. Impure functions are the ones that made that meme popular. So if pure functions are so great, then why don't we just make all functions pure? Well, by definition, pure functions can't have side effects. And a program that has no side effects is effectively useless. It just makes your computer heat up, but to no result. If your program has no side effects, it can't even print to the console. It can't access the internet. It can't update a database. It can't even draw buttons on a screen. So what should you do? Well, my rule of thumb is I try to make as many of my functions that can reasonably be pure, I try to keep them pure. And I try to keep the number of side effects in my code contained to just a few places, usually somewhere near the top level of my code. That way, when other developers are working with my code, it's obvious where the side effects are, and everything else is fairly easy to test and debug.
Pure functions. If you take nothing else away from this course, please take this. Pure functions are fantastic. They really are. They always return the same value given the same arguments, and running them causes no side effects. Side effects is something you'll hear pretty often in functional programming because we don't want them. Side effects, I'm sure we'll get into it in a little bit. Pure functions don't do anything with anything that exists outside of their scope. Okay, so if you have a pure function, you have an x, you give it to the function, you get a y. An impure function might modify an a, it might take in a b, it might take in a c, and it might modify a d. And then it also might output y. So you could see how if you're trying to figure out what's going on with a, it becomes a little harder to debug because where did it get changed? What function did it go into? So here's an example of a pure function. Find max, we have the min value for nums and nums. We make a float from -infinity, and then we're going to get the max value, just looping through. So then impure function takes a global. This is a pretty contrived example, but because why would you? But regardless, you change the global, and at least Python has this global keyword that cues you in to know that you're modifying something, that you got some side effects going on. All right, there's a bug in convert file format function. As it stands, it depends on some data that isn't scoped locally within the function. Those global values are mutated by external functions and are not guaranteed to be the same every time convert file format is called. We need to fix the bug by making convert file format a pure function. So for this one, pretty easy here because, I don't know what those other functions are doing, but we're just going to say, no, you don't get to do that anymore, and run it in here. And we pass, just like that. We take away the globals and we move it inside the scope of our function, making this a pure function. Let me submit. Good to go. All right. Pure functions have a lot of benefits. Whenever possible, good developers try to use pure functions instead of impure functions. Remember, pure functions return the same result. They're deterministic. Another thing you'll hear in functional programming quite a bit. You get an input and you give an output. They do not change the external state of a program. They do not perform any I/O operations. That is a side effect. So these properties result in pure functions being easier to test, debug, and think/reason about. Refer to the following examples and answer the questions. So example 1, is it pure or impure? Well, I don't see any outside state being modified, so it just takes in some numbers and it outputs a result. So we can say that we're only affecting products. We're not affecting the numbers. So it is pure. In example 2, we have a balance of 1,000. We have cars equals an empty list. And then we pass in a new car. We append cars. We change the balance. And we clearly are modifying global scope. So that example is going to be impure. Next question. So example 3, we have an import random. And then we're getting an input from random. Since we're using an outside object here to create our random int, that is impure. Chapter 3, Lesson 5, Reference versus Value. So when you pass a value into a function as an argument, one of two things can happen. It's passed by reference or it's passed by value. And reference means that it has access to the original value and can change it, or it's passed by value and the function only has access to a copy. Yeah, there's definitely more nuance than that, but sure. These types are passed by reference, and this is in Python. It's a list, a dictionary, and a set, and these types are passed by value. We got ints, floats, strings, bools, tuples. Most collections are passed by reference, and most primitives are passed by value. Let's go straight to the assignment. We have a way for doc-to-doc users to set their supported formats in their settings. In memory, we store those settings as a simple dictionary. Okay. Unfortunately, there's a bug in our code. When a new format is added or removed, it not only updates the new dictionary, but it changes the defaults themselves. That's not good. We want to create a new dictionary with the updates, not change the original. So for this one, the answer is pretty much in the tip. And you're going to have the add format. And we're basically just going to copy that, return the new one. And then in remove, we're going to do the same thing. We can say formats equals default formats.copy. And the key is we don't want to be modifying the dictionary that's being passed in because we don't, that's passed by reference. So we modify it there. Something else could be modifying it from somewhere else. And we want to make sure that it's a new copy of it. This does have some performance implications if you're working with very large dictionaries or collections, but that's a whole different topic. And we are good to go. So we have passed by reference and purity. Because certain types in Python are passed by reference, we can mutate values that we didn't intend to. This is a form of function impurity. Remember, a function should have no side effects. It shouldn't modify anything outside of its scope, including its inputs. It should return new copies of inputs instead of changing them. That example we just did. So why do we care about that, though? This is good because the big difference between good and great developers is how often they incorporate pure functions in their code. Pure functions are easier to read, easier to reason about, easier to test, and easier to combine. Definitely easier to test if you care about that kind of thing. And you should. Testing pure functions is much, much easier because you don't have to worry about other functions changing the value on you. Even if you're working with imperative language, you can and should write pure functions whenever possible. Yep, there's nothing worse than trying to debug a program where the order functions are called needs to be just right because they all read and modify the same global variable. So a pure function can mutate its local variables, mutate its inputs, mutate global variables, or call functions that mutate global variables. It can do none of the things. It can't mutate inputs. It can mutate only its local variables. So pure functions should be avoided at all costs, execute faster, or are easier to debug, read, and test. That one. It's easier to debug, read, and test. Input and output. It's avoiding side effects, comic little side effect humor. All right. So we're talking about I/O here. It refers to anything in our code that interacts with the outside world. Outside world just means anything that's not stored in our application's memory, like variables. So if we're reading from or writing to a file, simply printing to the console, reading from a database, or accessing the internet, all I/O is a side effect. This is great. Side effect. I told you we'd be getting into side effects, and here we are getting into side effects. So we frequently need to change the casing of some text. For example, we have title case, lowercase, uppercase. There's an issue in the convert case function. Our test suite can't test its behavior because it's printing to the console instead of returning a value. So for this one, all it looks like we really need to do is instead of printing these values, we need to be returning them. Kind of silly, but sillier things have happened. So we run that. Easy peasy. Done and done. On to the next one. So little SpongeBob meme humor with I/O and side effects. But in functional programming, I/O is viewed as dirty but necessary. We know we can't eliminate I/O from our code, so we just contain it as much as possible. Yep. So if the idea here is that you like if you're doing something useful with a program, you're going to have some impure functions when you do I/O. Beyond the scope of this walkthrough, this video, there are ways to manage those nicely, but for the purpose of this video, the idea is that you want to contain them to very isolated parts of your code, preferably, like this one's showing at the beginning and the end. So everything in between is pure. So if we have I/O IO should be blank in functional programming. Should be strewn through all throughout the project. Only used when Simon Peyton Jones isn't looking. Limited to specific parts of the code base or avoided completely. And that's limited to specific parts of the code base. There we go. And from the user's perspective, a program with no IO, it does nothing. It pretty much, that's not entirely true. Depending on who your user is, to be clear, it's not technically correct, which is the only kind of correct. But for this purposes of most things, yeah, you need IO. From an application perspective, it does nothing. Speaking of doing nothing, a no-op does nothing. It's an operation that does nothing. If a function doesn't return anything, it's probably impure. If it doesn't return anything, the only reason for it to exist is to perform a side effect. An example no-op is this useless computation here. An example side effect is here. All right, so this doesn't return anything, but it does modify y. Okay, we have talking about the global keyword. So in this assignment, we're going to complete the remove emphasis from line, and remove emphasis from word functions. They are currently no-ops. Yeah, they're just commented. So that's the parent function. It takes a full document, removes any single or double asterisk characters that are at the start or end of a word. So that's the emphasis in Markdown. And it should remove those. And then we're gonna, with the helper functions, they'll make remove emphasis function much easier to write. So we have remove emphasis from line, remove emphasis from word, and then remove emphasis from the whole document. For the sake of practice, try it without the replace string method. I used some of these built-ins. I being Lane again, I'm pretty sure. But okay, so we have split, strip, map, and join, which we've learned all about. We should be good to go here, right? This one's going to be, so to remove it from the word, all we need to do is return the word, and we're going to strip from both sides. So we're not L strip or R strip, just strip. And then to remove it from the line, we can split the line. So we can say words equals line dot split. I think by default it splits on the space, but just to be sure. And it's nice to be, I think it's nice to be explicit. So then we have our new words, our updated words, whatever. And that's going to be, we're going to map remove emphasis from word to each word. So we're going to pass in words. Let's make this a little wider. And then we can do joined equals space dot join, and we're going to pass in our new words and return joined, right? Now for this one, I think, so what we need to do is say lines, and that's going to be the doc content split on the new line. So get every line, and then we're going to get our new lines. I don't like that. Let's call it updated lines, because new lines means something different. Updated lines, and that's going to be, we're going to map same kind of thing, just remove emphasis from line to each one of the lines. And then now we need joined equals to have the new line dot join updated lines. And then we can return our joined lines. Just like that. Not too hard. Boom. First try. Memoization. At its core, memoization is just caching. In memoization, you can compute a value, store the value, and then instead of having to compute it over and over and over, or all the way up to get the, usually you use this when you're computing, you need to reuse the same values over and over. So instead of recomputing like something that takes a lot of resources, you can save the value after you've computed it the first time, and then just look up that value to get it again instead of recomputing it again. Again, kind of outside the scope, but it really trades like space for time. You gain time efficiency and you lose some space efficiency. You use a little more memory to get a little faster. Usually a lot of it faster. But you only want to do it when you need to. You really want to be certain that trade-off is worth it. Okay, so we're counting the words in a document can be slow, so we want to memoize it. Complete the word count memo function. It takes two inputs, a document string and a memos dictionary. And the keys are full document strings, and the values are the word count of the document. It should return two values, the word count of the given document and an updated memos dictionary. So it gives us the steps right here. pretty much tells us what to do right step by step for this one. So we create a copy, so we can say memos equals memos.copy, because we know we don't want to be modifying the input to our word count memo, right? We learned that. And then so if document is in the memos, then we can just return that word count. We return the updated memos dictionary. So we look that up by going memos, document, and then we return our new memos along with it, just called memos. Otherwise, we can use the provided word count function to count the words in a given document. So we can say the count equals the word count of the document. And then we're going to take our memos and we take the document. That's what we're keying it by, and that's going to equal count. And then all we need to do is return our count along with the memos. Just like that. Easy peasy. Yeah, spam, 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 and baked beans and spam. Boom. This is a little bit of a doozy. We have referential transparency. Pure functions are always referentially transparent. That's a fancy way of saying that a function call can be replaced by its would-be return value because it's the same every time. So referentially transparent functions can be safely memoized. So you have add 2 and 3 can be replaced by 5. The great thing about pure functions is they can always be safely memoized. Should you always memorize? No, we just told you. We just talked about this as a trade-off. You got memory and speed. It can be fast, but it uses more memory. So which of these is not equivalent to the others when evaluated? We have add 2 to 3, that's going to be 5. We have 5. We have 3 plus 3 minus 1, which is 5. And we have string 2 and string 3, which is not the same. And so memoization trades speed for better memory usage or memory usage for better speed. And that's going to be it trades worse memory usage for better speed. All right, chapter 4, lesson 1, recursion. Classic recursion. Recursion is a famously tricky concept to grasp, but it's honestly quite simple. Don't let it intimidate you. A recursive function is just a function that calls itself. Recursion is the process of defining something in terms of itself.
Recursion is a word used to strike fear into the hearts of new programmers. It's a simple concept that just takes a second to learn how to use properly. Recursion is just when a function calls itself. Now, that might sound fairly straightforward, and it is, but it is one of the hardest concepts for new developers to learn. So don't beat yourself up if it takes just a little extra practice and a few more examples before you fully understand what's going on. Let's take a look at this simple example. We've got a function called countdown, and it takes as input n, an integer. First, it just prints n. After it prints n, it calls itself again, but only after subtracting 1 from n. So what happens if we call countdown and pass in 5 as n? Well, first, 5 is printed to the console. Then countdown is called again, but this time with n minus 1, or 5 minus 1, which is 4. So we go back to the top of the function. Now we'll print n, which is 4. Call countdown again, this time with 3. And on forever. So we've figured out the recursive part, but the problem is this function will never stop.
I can't stop.
It will keep calling countdown over and over and over, decrementing by 1 every time, even into the negatives. Countdown with -1, -2, -3. So what we need is a base case to stop the recursive madness. Let's add an if statement to the top of the countdown function. If n is less than or equal to 0, instead of printing n and recursing again with n minus 1, we'll just print the word blast off to the console and return immediately, again stopping the recursion. So what happens now if we call countdown with n of 5? First, 5 is printed, then we call countdown again, and that's because 5 is greater than 0, so we're not going to trigger that base case. Next, countdown is called with an n of 4. Again, we're skipping the base case because n is greater than 0, 4 is printed to the console. This continues all the way down until n is less than or equal to 0. So when n is 0, we'll enter that if statement, print blast off, and then return. And because we're returning, there will be no more recursive calls to the countdown function. So the final result is that when we call countdown of 5, 5, 4, 3, 2, 1, blast off is printed to the console. Now let's take a look at one more example. Let's say we want to write a function called dictDepth that returns the depth of an arbitrarily nested dictionary. For example, this dictionary only has a depth of 1. It has 2 key value pairs, but there's no nested dictionaries within it. But if you take a look at this dictionary, it has 3 nested levels. Melee weapons corresponds to a second dictionary, which has the key stabbies, which corresponds to another nested dictionary, a total of 3 levels. Now, because the dictionary passed into our function can be arbitrarily deep, recursion is a really good fit for this problem. So let's figure out what our function signature should be. We'll define the new function, we'll call it dictDepth, and we'll pass in 2 parameters, d, the dictionary itself, and then max depth so far, which is just going to keep track of how far into the nested dictionary we are at each level of recursion. Now this time, let's start with the base case, just so we have a different way of approaching this problem. And our base case should be when there's no more dictionaries to recurse into. So if d is not a valid dictionary, for example, if it's just a number, like the number that corresponds with the Bose key, 6, then we're going to stop recursing. So we'll just add this if statement that says, if d is not a valid dictionary, immediately return the max depth so far. Okay, now we need a recursive case. We need to figure out how to go from the top level dictionary to the next level nested dictionary, or dictionaries, because there can be multiple key value pairs. So first, we'll set a current max variable equal to the max depth so far. And the purpose of this variable will be to keep track of the max depth of all the nested dictionaries at this level. Next, we need to iterate over each potential dictionary at this level. In Python, there's a .values method that we can call on a dictionary object to get every value in that level of the dictionary. Now, at each key value pair, we'll recursively call dictDepth, but this time we'll only pass in that nested dictionary. So instead of passing in D, we're going to pass in V. We also need to increment the max depth so far by 1 because we're going 1 level deeper. Now, once that recursive call returns, it will return with the maximum depth of that sub dictionary. So we should track that max depth, and at the end of the loop, if that max depth is the greatest of all the nested sub-dictionaries, that will be the one we'll return. So with the first call to dictDepth, we're going to pass in a dictionary, D. As you can see, it has 3 nested levels. The first key, melee weapons, is the only key in the top level. It corresponds to a dictionary which has 2 entries, stabbies, which corresponds to another dictionary, and bows, which corresponds to the number 6. Within the stabbies dictionary, the third level, we've got 2 keys, spears and knives, each corresponding to a single number. We'll also pass in a max depth so far of 1, because by default, a dictionary just has 1 level. So what happens? Well, first, in this initial call to dictDepth, the base case is going to be skipped because we passed it a valid dictionary. Next, the current max we'll set to the maximum depth so far, which is 1, and that will be overridden within our loop if we find a recursive call that returns a greater number. Now we iterate over all the key value pairs in the dictionary, which in this case is just the melee weapons key. We enter the recursive call where we pass in the dictionary that corresponds with the melee weapons key, that sub-dictionary. We also increment the max depth so far to 2. Within that recursive call, again, D is a valid dictionary. So we'll set the current max to 2, which is what the max depth so far was. Then we'll iterate over each key value pair again. This time there are 2. The stabbies key and the bows key. Because the stabbies key is first, we'll start there. We'll kick off another recursive call, this time passing in the dictionary associated with the stabbies key. We'll also increment the max depth so far to 3. We'll iterate over each key value pair. Again, there are 2, spears, 4, and knives, 3. Starting with the spears key, we move into another recursive call. This time, the value 4 is not a valid dictionary, so we trigger the base case and immediately return 4, which was the max depth so far that we passed in after incrementing it. Now we're back up a level after returning 4. We move on to the next key in the dictionary, the knives key. Again, it kicks off a recursive call. The max depth so far, again, is 4 because, again, we've incremented it from its parent function, which was 3. Again, D is not a valid dictionary, so we'll immediately return 4. Now, back up again in that parent function. We've iterated over both key value pairs, and we're going to return the maximum of the 2 return values, which, because they were both 4, is just 4. So that will return up the call stack again. Now we're back into the second call. There's another key for us to process, the Bose key. That will kick off a recursive call. This time, D, again, is not a valid dictionary. It's just the value 6. So we'll return 3, because 3 is the max depth so far after incrementing from its parent function, which was just 2. Now we've iterated over each key in the dictionary, the Stabby's key and the Bose key. The recursive call to the Stabby's dictionary returned a 4, while the recursive call to the Bose key returned a 3. So this call will return the maximum of the 2, which is 4. Now we're back in the original function. We've iterated over all the keys, which in this case was just the melee weapons key and its associated dictionary, and we'll return 4. And the recursion is done.
So we got to solve a small problem, then we call the function, we recurse, we have a base case, that's how we get out of it, done and done. Yeah, I can understand how it can be tricky. You have a function and you have a base case and you call the function inside of itself with less items or less, a smaller number, something that leads you to the base case. So for this one, doc2doc can automatically generate various layouts for a page. There are a lot of possible layouts. So we need a factorial function to calculate the total number of possible layouts. A factorial is the product of all positive integers less than or equal to a number. For example, 5, read 5 factorial, is 5 times 4 times 3 times 2 times 1, which is 120. Complete the factorial R function. So here's our tips for this one. What's a small problem you can solve first? How can you go from first value of x to the next value of x, all the way down to the last value? What's the base case? And since 0 is an empty product, what should an input of 0 return? See what empty product means here. This isn't going to be helpful at all. So the idea is that if x equals 0, what should it return? And the answer to that is 1. So if x equals 0, then we are going to return 1. Otherwise, we're going to return x times the factorial with x minus 1. And so what we're doing here, we're calling factorial again inside of itself, but every time we call it with 1 less, meaning eventually x will equal 0, right? And so that means the result of this, when it gets to 0, will be 1, and we'll finally return x times 1. And the x will be the result of the factorial for that. I hope that makes sense. Let's see if we did it. And we did. On to the next one. A little D&D humor. What happens if a recursive function has no base case? It's no longer considered recursive. It will keep calling itself forever, resulting in an infinite loop. Or Alan Turing comes back from the dead to haunt the author. Who's the author? The author? Is that Lane again? All right. It will keep calling itself forever and resulting in an infinite loop. So what is printed if I call, who's I? Print chars? Elephant 3. We go down here to print chars. If it's I equals the length of the word, we just return because this is a side effect. It's only IO, doesn't return a value. So it prints the word index of I. Otherwise, it prints chars word I plus 1. Basically, it starts at the word of the index. If the index is 3, that means it's going to skip the first 3 letters and we're going to get fant. All right, next one. Zip map. Let's practice another simple recursive function. You may not understand recursion just yet, but by following the instructions, you will begin to grasp the fundamentals. Within the doc2doc, we need to map certain properties from one document to properties of another document, so we can complete the recursive zip map function. Okay. It takes 2 lists as input and returns a dictionary where the first list provides the keys and the second list provides the values. So it's used like this. We can see how it's used. Good. Here's the pseudocode. If either the keys or values list is empty, then we return an empty dictionary. That's the base case. So we can just start right out by saying if the length of keys equals 0 or the length of values equals 0, whoop, wrong language again, then we just return an empty dictionary, right? Otherwise, we're going to recursively call zipmap on all but the first elements from keys and values. Then we add the first element of keys to the resulting dictionary and set its value to the first element in values and return the updated dictionary. Okay, so let's not get ahead of ourselves. Let's call this updated equals to zipmap. We need to call that on the keys. What does it say? All but the first element. And then we have the values. Wait, all but the first element. So that's the opposite of that. So we need all but the first, starting from index 1 and going to. So that's that syntax. It means start here, go to here. If you don't provide it at beginning, then it starts at 0. If you don't provide an end, then it goes till the end. So we need to start at 1 and go till the end. So we have updated, and then we have keys 0 equals values 0, and then we return the updated dictionary. Sounds good. Let's see if we did it. We did it. All right, this one's a little more complex. Yep, difficulty 8, so a little more complex here. Again, you could also use dictionary comprehension here to do what you want, but beyond that, pretty straightforward still. The idea here is that we're calling this with just the index from the first, without the first one in each one, all the way to the end. So every time it runs, it keeps doing that. And then eventually we'll run out of keys or values, in which case we return an empty dictionary. That's our base case. All right. Good to go. Consider the following function. We have countdown with print n. If n equals 0, we return. Else countdown n minus 1. So which line contains the base case? Pretty easy to understand. If n equals 0, that's our base case. Which line contains the recursive call? Well, that's going to be where we call countdown again with n minus 1. And what would happen if we swapped countdown n minus 1 for countdown n? So if we didn't do n minus 1, then we're just calling countdown with n again. Nothing changes with the input. That's the big important part, is if you're going to call the function again, then the input needs to change, or else you're just going to result in an infinite recursive loop. It will not be more elegant. It will not speed up the function execution. It results in an infinite recursive loop. Nested sum. Recursion is hard for all new developers. If you're struggling, that's okay. Take your time. That's why we're doing a few extra practice problems. So for this assignment, we have users can process files or entire dictionaries. We need to know the total size of those files and directories measured in bytes. Due to the nested nature of directories, we represent a root directory as a list of lists. Each list represents a directory, and each number represents the size of a file in that directory. For example, here's a directory that contains 2 files at the root level, then a nested directory with its own 2 files. So here's a more complex example. You have the root, and then you have this file, it's 5 bytes. You have a directory, contains 2 files that are 5 and 7 bytes, directory that contains a directory with 2 files that are 8 and 9 bytes, and a file with 10 bytes. Yep, so you have a root, here's our scripts, and then here's our directory of characters with Zuko and Ong. And then I've never seen Avatar, sorry. And then we have our seasons directory, which has a directory of season 1, and then the Avatar Returns and the Southern Air Temple, 9 bytes. And then the season 2 notes.txt. All right, so we complete the sum nested list function. It takes a nested list of integers as input and should return the total size of all files in the list. It's a recursive function. Here's some pseudocode to help you get started. Okay. So for tips, we can use loops with recursion. While function programming avoid loops, recursion can be used outside functional programming. And we can use the built-in is instance. That just does pretty much what it says. We can check if something's like an int or a list, and we'll use that here. So this is not going to be, this isn't going to be very functional. So we're just going to say total equals 0, right? And then for every element, in LST is what we're getting in here. So for every element in the list, we want to check if it's a directory, which would mean it's a list. So if it's a list, meaning is instance, I think L and list, we're going to add to the total the sum of the nested list with the element, with the L here. And then otherwise, all we need to do is add to the total. And we're going to say plus equals the L. And so if it's a list, we need to recurse inside that list for every, for if it's a directory, we need to go inside that directory for every file in there. We're going to add it to the total. And this is another common use case for recursion. It's great for trees and stuff where you don't know the structure exactly, or it might be nested all the way, we don't know how many levels deep it could be nested. And we're going to return the total. And we could actually do this. I think we could, sorry, just using this as a chance to see if I could do Python better. And so plus equals the sum of nested list if the instance is a list else L. You could do it like that too, I think. Yeah. Boom. Not that that's like any better. I'm just trying things out, Okay. So here's our review. Recursion is so dang useful. You just know that's Lane. It's so dang useful with tree-like structures because we don't always know how deep they're nested. Yeah, see, that's about going. Stop and think about how you would write nested loops to traverse a tree of arbitrary depth. It's not easy, is it? Yeah, you just nested loops all the way down. I most often see there's the I again. I most often use recursion on tree-like problems, file systems, nested dictionaries, etc. If I'm just iterating over a one-dimensional list, then a loop is typically simpler, even if it's not as pure in the academic sense. So remember, the rules of functional programming are just philosophies to help you write better code, but it's not always the right tool for the job. The same goes for any programming paradigm. Yes, very true. So what makes it hard to loop over a tree? Is it that we don't know the depth of the tree, the number of nested levels, or we don't know the breadth of the tree, which is the number of items at each level? Or that trees have too many items in the initial list? Or loops are hard for my smooth brain? That is, we don't know the depth of the tree, but they are hard for my smooth brain. Imperative loops are allowed in purely functional code. No, definitely not. And the next one, loops are used often by good programmers, even though they break the academic rules of functional programming. Depending on the language, it's not even possible sometimes. But sure, yes. There we go. Lesson 12, recursion on a tree. Recursion is often used in tree-like structures. For example, nested dictionaries, file systems, HTML documents, and JSON objects. That's because trees can have an unknown depth. It's hard to write a series of loops because you don't know how many levels deep the tree goes. So in this assignment, we're responsible for a module in Doc2Doc that can scan a file system, represented in our code as nested dictionaries, and create a list of file names. Complete the recursive list files function. It accepts two arguments, the current file tree, which is a dict, and that's a dictionary representing the file system, and the current path. It's a string representing the current path. Got it. It should return a list of file paths. For example, this file tree should result in the following list of paths. So we have documents as a base, and then we have proposal.docx, and we have receipts, we have January as a folder. All right, it keeps going down, adding to the string. So we create an empty list to store the file paths. Okay, let's call this file paths, right? And then usually we can call this like a file tree node. It's for each node in the current dictionary. So for each node in the current file tree, we are going to check if there's any nested nodes, right? If the nodes entry is none, it's a final file, not a directory. Okay, so let's go back and look at this. So if it's none, that means it doesn't have any nested stuff. Let's call this next, and we'll say that's the current file tree index of node, right? If next is none, then we're going to take our file list, get the current path, right? So what we're going to build on. So we have the current path. What we're going to do is we're going to append the file paths. Again, not very functional. This isn't very functional. I'm just saying, but that's fine. And then we're going to have the current path, and then a slash, and then the node. Right. Okay. Otherwise, we're going to extend. Let's look at how to use extend. So extend the list by appending all items from the iterable. Okay, so it's a list.extend. Otherwise, so we say else, we have file list, file paths extend, and we're going to call this again. So call this files equals list files, and we're going to go next, and then we're going to call that with the current path. We'll do an F string again, current path, and then the node. Cool. So then we're going to extend with files. Let's call this next file paths, right? Put on here, change that. Let's make this a little wider. All right, this one is a little challenging. And again, we're not really using functional, we're just using loops here, but recursion is the concept we're trying to drive home here. Let's call this next file tree. There we go. All right, so the next file tree, if it's none, otherwise we're going to list files, and we're going to call list files again with our next file tree. So that's, we're going down now, and deeper and deeper, deeper and deeper. And then we have the current path and the node, and so that's right now current path equals an empty string, but the next time it's called, it'll equal the path up to that current file tree. And then we extend that, and then we can just return. Oh, I've already got it. Return file paths. If we run that, it should pass. A little bit more complex. Let's see. That was it's a 10 difficulty. So yeah, but still, I think we still got it, right? Very, very recursion, just so useful for trees, for nested structures that you don't know the depth. That is, this is kind of a classic way to use it. You set an accumulator, right? Just like we might even be able to replace this, if we wanted to. If we wanted to go about refactoring this to be more functional, we could, for instance, do like maybe a reduce. We could part this out into a separate function of its own, but we're not going to do all that. All right, on to the next one. The dangers of recursion. Recursion is great because it's simple and elegant, often being the most straightforward way to solve a problem, but there are some things to watch out for. Stack overflows. Each function call requires a bit of memory. Just a little bit. So if you recurse too deeply, you can run out of stack memory, which will crash your program. That's what the famous website's named after, TIL. If you don't have a solid base case, you can end up in an infinite loop, which will likely lead to a stack overflow. So recursion is often slower, that's especially in languages like Python, than a for loop because each function call requires some memory. Tail call optimization can help with this, but Python doesn't support it. So which is typically more performant in Python, a regular old for loop or a deeply recursive function? That's going to be a regular old for loop. Alrighty. I'm Tech Savvy Travie. Nobody calls me that. Well, see you when I see you. Function transformations. Function transformation is just a more concise way to describe a specific type of higher order function. It's when a function takes a function or functions as input and returns a new function. So we know we've had higher order functions before this where we took in a function as a parameter, and this is the other type of higher order function, which is you return a function, and usually some sort of modified function based on the parameters that you're passing in. So in this case, you have this nice little diagram here. So you have a mul function, an add function, and you have a self math function that takes those functions and outputs a square function and a double function. Okay, so here we see that, and we see multiply and add, and then we have self math, which takes in a math func and defines an inner func, and then returns the math func over x of x. So the function you return will take an x value and do a thing with it. So in this case, square would equal self math multiply, and then double would be add. All right. So the self-math function takes a function that operates on two different parameters, for example, multiply or add, and returns a new function that operates on one parameter twice, for example, square or double. So for the assignment here, doc to doc, needs a good logging system so that users and developers alike can see what's going on under the hood. Complete the getLogger function. It takes a formatter function as a parameter and returns a new function. So we return a new function inside getLogger. See self-math example, okay? It accepts two strings. You can just name them first and second if you'd like. The logger function should not return anything. It should simply print the result of calling the given formatter function with the first and second strings as arguments. And then we return the new logger function for the test suite to use. The :delimit and -delimit functions are formatters that will be passed into our getLogger function by the tests. You don't need to touch them, but it's important to understand that when you call formatter in the getLogger function, you're calling one of these functions. Got it. So we will be defining a function. So we define like the logger, and that takes in a first and a second. And once I just keep getting reminded about Vim mode. I just keep getting reminded. Okay. So it prints the result of formatter on first and second. I think that's it. And then we return the logger. I don't know. I think that's right. Yep. Alrighty. Easy as that. So we have this as a function. And this is where I think, types are very handy because we don't know what formatter does. We don't know how many things it takes. On to the next one. Transformations review. Example of a function transformation. We have def multiply. Yeah. We know all that. We know what same thing we saw. What does the expression self-math add return? So if we pass add into self-math, what does that return? Is it an integer, a function and an integer, a function, or two functions? What do y'all think? Are you with me? Are you with me out there? Oh, right. Good call. All right. So what does the expression self-math add return? Is it an integer, a function and an integer, a function, or two functions? And of course, it is a function. Woo! All right. And where can innerfunc be referenced directly? Is it within the global scope, within the add function, only within self-math, or anywhere? So we have innerfunc, and innerfunc is defined inside self-math, so innerfunc can only be accessed or referenced inside self-math. There we go. On to the next one. All right. Here's some example code for you to reference as you work through the assignment. Yeah, but this is the same example code. Okay. All right. The assignment is complete the doc format checker and converter function. It takes a conversion function and a list of valid formats as parameters. It should return a new function that takes two parameters of its own, the file name and the content. So it's the name of the file to be converted, and the content is the content or body text of the file to be converted. So we have a conversion function and a valid formats. So if the file extension of the file name is in the valid formats list, then it should return the result of calling the conversion function on the content. Otherwise, it should raise a value error with the message invalid file format. Tip, I used the split method on the file name to get the file extension. You can use the in keyword to check if a value is in a list. The capitalized content and reverse content are conversion functions that will be passed into our doc format checker and converter function by the tests. All right, let's bring this over a little bit so you can see more what we're doing. At least just get it on the screen. All right, we need to return a new function. I like to call, when I do this, I think it's just taught in OCaml first. This kind of convention doesn't really matter, but I like to just call it aux, whatever. And then so it takes two parameters of its own. It takes a file name and it takes a content. And if not file name in valid formats, it's going to raise, not throw, wrong language, a value error. So raise value error of invalid file format. Otherwise, it should return the result of calling the conversion function on the content. And then we return aux, right? See, zero passed, two failed. Okay, let's see what we did wrong. Why is it doing this? If the file name is in the valid formats list, wait, if the file extension of the file name, so I need to get the extension. X equals, so that's why I said use the split method. Okay, file name dot split, split on the dot. Okay, and then if the X is in there we go. By the way, not a great or reliable way to get the file extension, but it is a way. All right, on to the next one. Okay, so why transform? You might be wondering, when would I use function transformations in the real world? Isn't it simpler to just define functions at the top level of the code and call them as needed? Good questions. To be clear, we don't just transform functions at runtime for the fun of it. We only use advanced techniques like function transformations when they make our code simpler than it would otherwise be. So, code reusability, creating variations of the same function dynamically can make it a lot easier to share common functionality. Take a look at this formatter function. It accepts a pattern and returns a new function that formats text according to that pattern. So we have our formatter that takes a pattern, and we have an inner func, which I called aux earlier, that takes some text. It has a result, and then it checks if the pattern is equal to this. It adds that to the result. So you could pass different patterns into it and create new formatters easily. You have bold formatter, a formatter with the 2 asterisks, italic formatter with 1 asterisk, and a bullet point formatter with, the starting asterisk. And then use them like this. Bold formatter, hello. Italic formatter, hello. Bullet point formatter, hello. Closures. 90% of the time when I use function transformations is because I want to create a closure. We'll talk about closures in the next chapter. All right. Not to be used willy-nilly, but if you're reusing a lot of logic, then you can, kind of have like something like a pattern in this case where you can create a function inside of it that works over any kind of pattern. Makes sense. So we should use function transformations blank when it results in more understandable and extendable code. Never or always. Real tough one here. But I'm going to go when it results in more understandable and extendable code. So the next question is, couldn't we just explicitly define bold formatter, italic formatter, and bullet point formatter as normal functions? Yeah, we could. And to be clear, in my opinion, if you find yourself repeating something a single time, repeating that logic, go ahead and write it. It's when you have multiple different instances of shared logic and you start to find yourself repeating a lot of things, don't abstract too early. Abstract when it makes sense. So yes, you could, but it would require more code. Or no, this is the only way. In certain cases, the case can be made that this is the only way to do certain things, certain kinds of function transformations, if you wanted to do them dynamically. But in this case, it will require more code. That is Chapter 5, Function Transformations. Chapter 6, Closures. A closure is a function that references variables from outside its own function body. The function definition and its environment are bundled together into a single entity. Put simply, a closure is just a function that keeps track of some values from the place where it was defined, no matter where it's executed later on.
Closures are a way for your functions to keep track of state from function call to function call. Closures usually occur when one function is defined within another function, and that inner function references a variable that's declared in the outer function, one that's outside of its own scope. Take a look at this new counter function in Python. The first thing it does is declare a new count variable and set it equal to 0. Next, it defines an inner function. This function is defined within the new counter function, and we've called it counter. Now, the very first thing it does is use the non-local keyword to tell the Python interpreter, hey, I'm accessing a variable that's declared outside of my scope. So it's just making that count variable available to be accessed. Now, this is something that's fairly Python specific, the non-local keyword. You probably wouldn't need that in another language, something like Go, for example. Now, what it actually does is increment that count variable by 1. right? Count plus equals 1. And then it returns the new count. And then at the end of the new counter function, it returns the inner function. So it's actually returning a function as a value. To see how it works, let's create some counters. So first we'll call new counter and save the return value into a variable called add health. Now remember, new counter returns a function. Specifically, it returns that counter function. That counter function is now being saved into a variable called add health. Let's call it again, but this time we'll save the returned function into a value called add mana. If we call add health once, it will return 1 because it took that count variable 0, incremented it by 1, and then returned it. If we call add mana for the first time, it will also return 1. And that's because each function has its own copy, its own closure around a different count variable. Now, if we call add health a second time, this time it will return 2. And again, that's because the closure has enclosed around the count variable. So add health has its own copy of that count variable that it's going to increment with each successive call. So we can keep calling add health and add mana, and they'll both increment their counts independently. And that isolation is a key feature of closures and what makes them useful. One of the best parts about closures and what makes them useful in real programming is that they allow us to maintain state without having to change the function's signature. So for example, the add health function, it keeps track of and updates this count variable, but it doesn't take a count as input. That means if I have a place in my code where I need to use a function that doesn't take any parameters as input, but I still want to keep track of state, a closure might be a good fit. Now, the obvious downside to this is that the add health and the add mana functions, they're not pure functions, right? They're the antithesis of a pure function because they have side effects. They're mutating something that's outside of their own scope. When called with the same parameters, they produce different outputs. And again, that makes them impure. But the outer function, new counter, that is a pure function because each time you call it, you get a new fresh closure around that count variable that's essentially been set to 0. So if you want to write good unit tests for this type of function, the thing that makes sense is to create a new copy of the closure by calling the outer function at the beginning of the test suite, and then you're starting your test from scratch each time.
For example, the concatter function returns a function called docBuilder. Yay, higher order functions. That has a reference to an enclosed doc value. So you can see here we have concatter and we have doc. And we have docBuilder, which uses, this is the non-local keyword, and you see non-local. It tells you we can use it from the enclosing scope. And then you have doc outside of the function, but we can use it inside of the function. So maybe it changes here. We update it here, and we return the function using the value of the variable defined outside of there. It's kind of like a global variable inside, when you use a global variable inside of a function, but this is a case where we're using a higher order function to return another function. So the global is inside the enclosing function, if that makes more sense. So when concatter is called, it creates a new stateful function that remembers the value of doc, its internal doc variable. Each successive call to the Harry Potter aggregator appends to that same doc, okay? Easy peasy. Non-local. Python has a keyword called non-local that's required to access variables from an enclosing scope. Most programming languages don't require the keyword, but Python does. Doc2doc keeps track of how many words are in a collection of documents. Complete the word count aggregator function. It should return a function that calculates the number of words in its input. Okay? It should then add that number to an enclosed count value and return the new count. In other words, it keeps a running total of the count variable within a closure. Tip, I used split to count the number of words in the doc string. So first thing we want to do is we want to make a count variable that'll equal 0. And then we'll define our aux function. So then that takes a doc parameter, which is just a string. And then we can just go count plus equals doc.split on the white space on the space, and then we get the length of that, and then it returns the new count. So this returns count, and then we return aux, right? And so if we run that, one failed. Oh, so there we go. We got to say non-local count, and then we pass. See, we can't just use it like we would in other languages like JavaScript or what have you. So good to go. So the review, the whole point of a closure is that it's stateful. It's a function that remembers values from its enclosing scope even after the enclosing scope has finished executing. It's as if you're saving the state of a function at a particular point in time, and then you can use and update that state later on. Same example. That means that in many cases, closures are not pure functions. They can mutate state outside of their scope and have side effects. A closure blank the value of a variable outside its body. And that is, it cannot change the value or it can change the value. And the whole point of it is that it can change the value. That's right. It can change the value. A function that changes non-local variables is not a pure function, or it is a pure function. So if it can change non-local variables, is it pure or is it not pure? I just want to be pure. It is not a pure function. Ta-da! More clearly, though, this function that you return is not a pure function. However, concatter itself, is that a pure function? Because concatter always starts with a doc that has this, that's an empty string, and starts the state over. So concatter is itself a pure function. It just returns an impure function. All right, next one. Some closure practice. Remember, a closure is a function that retains the state of its environment. That makes it useful for tracking data as it changes over time, but it can come at the cost of understandability when not to use the non-local keyword. When the variable is mutable, such as a list or dictionary or set, and you are modifying its contents rather than reassigning the variable. Let's try a closure without the non-local keyword. Okay. Complete the new collection function. It accepts a list of strings, initial docs. It should return a function that closes over a copy of initial docs. This function should accept a string, append that string to the closed over list, and return the new list. Do not modify the initial docs list. Yeah. Okay. So we need to go initial docs dot copy, and then we have a def aux, and that's going to take a doc, a singular doc, and it's going to go docs.append. So it's saying I don't need to do that. So I can just append that and then return docs and then return aux. Am I understanding that right? No, I got to use the right variable names. There we go. Okay, so since docs is a list and we're not actually reassigning it, we're not like in that first one we had like a count that was equal to 0, and then we were doing like count plus equals, which we can say is that's reassigning to count. So in this case we have docs, which is a copy of a list. We append to it. We don't need the non-local because we're not reassigning to it, and we can just return it. And let's submit that. Done. Good to go. Another one down. If there's anything to take from this, don't take the Python from it. And if you can't tell, I'm like, oh, I don't need to use the non-local keyword here. Those are specifics to Python. That's not what we're trying to learn necessarily here. So that is closures. On to currying, which I think will be fun and an interesting concept to teach in Python. Currying. Function currying is a special kind of function transformation where we translate a single function that accepts multiple arguments into multiple functions that each accept a single argument. This is a normal 3-argument function. You have box volume with 3, 4, 5. And this is a curried series of functions that does the same thing. You have box volume, you call it, and that returns another function that you call with the next parameter, and that returns a function that you call with the next parameter. Here's another example that includes the implementations. So if you have sum of A and B, you return A, B, right? And you can pass sum 1, 2 to it. And then you have the same thing curried. So you have sum A, you do inner sum, that takes just a B, and then you return A, B. So kind of like in closures where you can use the value from out of the scope, from the scope above the function that you are calling. The sum function only takes a single input, a. It returns a new function that takes a single input, b. This new function, when called with a value for b, will return the sum of a and b. We'll talk later about why this is useful. In doc-to-doc, depending on the type of text file we're working with, we sometimes need to transform the font size of the text when it comes time to render it on the screen. Fix the converted font size function. We're using a third-party code library, EU, that expects our function to be a curried series of functions that each take a single argument. Right. Converted font size should just take a single argument, font size, and return a function that takes a single argument doc type. That function should return the font size multiplied by the appropriate value for the given doc type. Alrighty. So, converted font size should just take a single argument, font size. Right? Let's get this out of here. And then we def aux. That takes a doc type. Just pasting that in there. Same logic, right? Boom. And then we go over here. And then we return aux. I think that's all we need to do here. All right. It looks like we're good to go. Boom. Another 400 XP gained. We are building up that XP like crazy. Let's move on to the next lesson. Why curry? It's delicious, of course. Probably my favorite food group. I did a group of foods, right? It's just kind of the gravy. So why curry? It's fairly obvious that the def sum a, b, and return a plus b is simpler than def sum with a and then return inner sum b, a plus b. So why would we ever want to do the more complicated thing? Well, currying is often used to change a function's signature to make it conform to a specific shape. For example, def colorize converter doc, the colorize function accepts a function called converter as input, and at some point during its execution, it calls converter with a single argument. That means it expects converter to accept exactly one argument. So if I have a conversion function like this, marked down to HTML, I can't use it with colorize because it wants two arguments. To solve this problem, I can curry markdown to HTML into a function that takes a single argument, like so, as in the example here. All right, so this asks, when passing a function around to be called later, it blank how many arguments the function accepts. Does not matter or does matter. It does matter. That's right. It does. It does matter. And other languages like OCaml and Haskell, for instance, all of their function signatures, if you look at them, it might be confusing at first until you realize they all only take one argument. You know, when you call them with multiple arguments, it's actually doing the currying for you. And that way you can do things like called partial application. Call a function, if it takes 3 arguments, we can call it with just the first 2, and that will return a function that takes the last argument. In any case, moving on. So when should you curry functions in Python? Rarely, only when it serves a clear purpose. Never or always. It's going to be rarely. I will say, okay, sidebar. Could be argued always, but in Python specifically, rarely, only when it serves a clear purpose. I will say just that these quiz questions are a little too easy. They're made easy by the fact that the other answers are like extreme, and you can always know that the extreme answer isn't the one, right? So that's another 100 XP gained. A little currying practice here. Remember, currying is when we take a function that accepts multiple arguments, and we convert it to a series of functions that each accept a single argument. So now box volume 3 returns a new function that accepts a single integer, and returns a new function, box volume 3.4, that returns, and then box volume 3.4 returns another new function that accepts a single integer and returns a new function. Then box volume 3.4.5 returns the final result. Here's another way of calling it, where each function is stored in a variable before being called, with link 3, with 4, and final volume. And here are the function definitions. Yep, just all the way, it's functions all the way down. For the assignment here, doc to doc needs to be able to find the number of lines in a document that contain a specific sequence of characters. For example, given the following document, AAA, BBB, CC, DD, AAA, BB, how many lines contain the sequence AA? The answer is 2, AAA and AABB. So complete the line with sequence function. It should return a series of curried functions so that it can be called like this. The first one needs to return length, right? And so this needs to return a function that takes in doc, okay? The sequence is generated by the first with care that has been provided for you. It works like this. A, length 3, AAA. B, length 2, BBB. Character, length 4, sequence is da-da-da. You need to find and return a second curried function. I called mine with length. Yeah, sure. It should accept the final parameter, a doc string, and return the number of lines that contain the sequence. Okay? Define the with length function, so we'll just do that. Okay, and that's going to take a doc. We'll pass for now. Split the doc into lines. Use a loop, or if you're feeling fancy, use reduce to count the number of lines that contain the sequence in them. Return the count from the with length function, and then return the with length function from the with care function. Okay, so we need to split the doc into lines. So our lines is going to be equal to doc.split on the new line. And then we can say count equals 0, and for line in lines, if sequence in line, then count plus equals 1, right? And then we return count. And then from here, we return with length function. And then we've already returned the with care function. Cool. And I think that will do it. And we'll check. 2 passed, 0 failed. We're looking good. And just to be clear, yeah, you could use a lambda function here and use reduce, but for simplicity's sake, we'll keep it like this. Sometimes it is easier to reason about iterative code. And we'll check our answer. Good to go. This is if you wanted to do it with reduce. So yeah, prev, cur, and previous. So we can call this accumulator too. We can change that to line. If sequence in line, then we have the accumulator and our initial value over here. That's going to be our accumulated value. And then line is the next one over each element in lines. Easy peasy. Else back. Submit. Good to go. We've done it again. Python's one of those languages that's really easy in the editor stuff because you have all the autocomplete, and like if I type reduce, I'll get like the auto import for it and stuff. But there are a lot of weirdness to some of the built-in functions and built-in methods and stuff like doc.split. I would expect this to be, honestly, lines.reduce, right? That would make more sense to me. But neither here nor there. Decorators. Decorators are just syntactic sugar for higher order functions. Damn. 3 keywords, 3 terms in a row. All right. That's not exactly what decorators are. He's talking about Python decorators. That's okay. Because you also have like the decorator pattern, right? And for example, we have a definition of a vowel counter with the func to decorate. We have a vowel count 0. Ooh, a little closure action. And we have the definition of a wrapper that takes a doc. We use the non-local vowel count. We have our vowels, A, E, I, O, U. And then for each character in the document, if the character is a vowel, then we count the vowel. We increase the count by 1. And then we print our vowel count, making this officially an impure function. Well, it was already impure because we're using non-local, but now we have another side effect. Cool. And then we return the func to decorate with doc passed in. And then we return that wrapper. And then in Python, the syntax is you can use this at vowel counter to automatically decorate, automagically, very much a little magic going on. It will automatically wrap this, right? And now, so one of the things you can do is I know that there is a partial. And so this will, if you use the decorator partial, then you can basically, do the auto currying partial application thing for you, which is kind of nice. So you have to return all those functions that just return another function that just return another function, right? The vowel counter line is decorating the process doc function with the vowel counter function. The vowel counter is called once the process doc is defined with the at syntax, but the wrapper function that it returns is called every time process doc is called. That's why vowel count is preserved and printed after each time. It's just syntactic sugar. Decorators are just another, sometimes simpler way of writing a higher order function. These two pieces of code are identical. With the vowel counter decorator, or without the decorator, we have a vowel counter, which is a higher order function that takes process, and we can do it the same way, right? I've shown this before with trampolining, which is how a way to avoid stack overflows when languages that don't have tail call optimization for recursive functions. In Python, you could just put trampoline and decorate it, all good to go, right? So for this assignment, the provided file type aggregator function is intended to decorate other functions. It assumes that the function it decorates has exactly 2 positional arguments. And we're going to create a process doc function that's decorated by file type aggregator. It should return the following string: processing doc, file type, okay? Where doc and file type are its positional arguments. See line 11 for where it's being called. Okay, let's tackle this problem. So we need, it says don't touch above this line this time. Okay, a little trickier. We need to make a new function. So we have file type aggregator. So we call this process doc, right? As soon as the function it decorates has exactly 2 positional arguments. So the first one's gonna be doc and the next one's gonna be file type, right? And then we're going to decorate this with file type aggregator. Not great syntax highlighting there, but that's okay. So does this need to, am I literally just typing that? Processing doc, I swear, stop telling me about Vim. Do I have to use Vim mode just to stop? Yeah, we're already at the end of it, so it doesn't matter now. But and then file type like that. I guess, is that all we need to do? I guess so. That's all we needed to do. They don't all have to be hard. And then we'll go ahead and submit. Good to go. Args and quargs. Quargs? Quargs. In Python, args and quargs allow a function to accept and deal with a variable number of arguments. So args collects positional arguments into a tuple, and quargs, with 2 asterisks in front of it, collects keyword or named arguments into a dictionary. So if we have print arguments with args and quargs, we print the positional arguments, you'll get this output. We'll get a tuple of positional arguments and then a dictionary key value pairs of the keyword arguments. Positional arguments are the ones you're already familiar with, where the order of the arguments matters, like this. With keyword arguments, they're passed in by name, so order does not matter. So if you have A and B, and you say sub B equals 3, A equals 2, we're still good to go, because these names matter, and you're passing them in by name. So any positional arguments must come before keyword arguments. This will not work. So you have to pass in your positional arguments before your keyword arguments. So for this assignment at doc to doc, we need better internal debugging tools. So we're going to complete the args logger function. It takes a variable number of positional and keyword arguments and prints them to the console. First, print each positional argument in order using numbers and periods as the prefix. Next, print each keyword argument in order using asterisks as the prefix with a colon between. For example, asterisk age colon 17. Use the sorted function to get the order right. Don't feel guilty using loops. Got it. And the items method can iterate over a dictionary. Yep. And that's going to be, if you do items, you'll get a tuple for each item that is the key value pair. And then the sorted can sort the dictionary. Here's how I would actually do this, because I don't think we've learned about enumerate yet. So I don't know, but we're going to use enumerate here. I think it's nice. Instead of having to maintain, because we would just do like I equals 0, and we could increment that. Or we can go for I arg in enumerate args, right? And then we can say print, and we're gonna do an F string. We're starting at 1, okay, good to know. And then we're gonna print so I plus 1 with a period and then the arg. That's our first loop. And then we're gonna do the same thing for KV, and for this one we just need to go in we do sorted just like in the example down here. Say sorted keyword args or kwargs dot items, and then for this one we print another F string. This one just takes an asterisk with the key and then a colon and then a value, just like that. And this doesn't return anything, it just prints. And that doesn't give us test results, it just gives us the output, but it seems right. So we're gonna go for it. Boom. And there you have it. Another one down, just like that. XP gained. It's just that easy, people. Yeah. Anyway, on to the next one. So the args and kwargs syntax is great for decorators that are intended to work on functions with different signatures. Log call count function below doesn't care about the number or type of the decorated function's func to decorate arguments. It just wants to count how many times the function is called. However, it still needs to pass any arguments through to the wrap function. So in here we have a log call count with the func to decorate, and then we have a count, and we're using closure here. So we have the wrapper, and we have the non-local count, and we increase the count plus 1 plus equals 1, and we print how many times it's been called, and we return the func to decorate with all of the args and keyword args passed through. Just kind of passing them through, all the arguments and keyword arguments. So for this assignment, we need to complete the markdown to text decorator function. It can decorate a function with any number of string arguments, no matter if they're positional or keyword args. It will run the decorated function, but first strip out any markdown heading symbols. See below for an explanation of markdown headings. It should return a wrapper function that takes the args and kwargs, and the wrapper should map the args to a new list where each string is converted to a plain text using convert MD to text. And then it's going to map the kwargs to a new dictionary where each value is converted to plain text using convert MD to text. The key should remain the same. So then we're going to return the result of calling the decorated function with the new arguments. Okay, so this one is a little bit, what is this? Yeah, it's a 10. So let's look at the tips here. Take a look at the editor's formatters.py tab. We can see what the formatter functions do. Okay. Yeah. Okay. Using the F string syntax I was using when I said I didn't know if that'd be cool. And then we have the map tips, the map function, the list function, the dict function. That's dict function. And the items method can be used on a dictionary to get an iterable of key value tuple pairs. Convert MD to text function takes a string of markdown text and returns a string of text with any heading symbols removed. So for example, we have this is a H1, then it just returns the text. H2 just returns the text. No heading gets nothing. No heading gets no change. So if it starts with, we strip anything like that out, but we don't have to do that function. So let's go back to it should return a wrapper function that takes args and kwargs, and it should map the args to a new list where each string is converted to plain text using the convert MD to text. Right. So here's how I would do this. We just return, so we have func, so we're just going to return func. So when we pass, if you look back, to pass them back in, we need to have the star and the double star. It's not really about what these are named. It's this magic star and double star, asterisk syntax that's going to actually do it. So to get this, we can pass in, we change it to a list. We map convert MD to text to the args, right? And then that's going to be the single asterisk. So that's because that's the args, not the kwargs. And then for the second one, that's going to be a dict. And then for this one, we're going to map over. So the key should remain the same. And so if we do use kwargs.items, we'll get the tuple of key value pairs, get an iterable of tuple pairs. So what we can do there is we'll make a lambda over item. No, wait. That's not the syntax. This is I always get that wrong. We're going to leave item 0, So what we're doing is we're getting a map. This is going to give us iterables, right? And then the dict here is going to take that iterable of key value pairs and is going to turn it into a dictionary. So we have this item 0, and then the second one we actually need to convert MD to text item index of 1, and then I might might pull that out like that. So then we can go, that's going to be quargs.items, right? And then so this is returning a tuple that is the key unchanged and then the value converted. Right. And then now we can pull that out, just inline it like that. Right. It's very elegant solution. Yeah, like I said, this one's a little more involved, so I'm not gonna pretend. I don't know. What are we gonna pretend? It's not. So we have a lambda that returns a tuple, the key value unchanged, and then the value converted from any heading will be just converted to text. Then we go ahead and return that wrapper. And let's see how we did. First try. And then we can submit. Boom. Done and done. A decorator is just syntactic sugar for higher order functions. Syntactic sugar just means a more convenient syntax. Not all programming languages have decorators, but most do support higher order functions and closures. Some of the famous functional languages like Haskell, Erlang, Clojure, and Lisp do not have decorators, but they do have higher order functions and closures. So if you understand those concepts, they will serve you well in many different languages. I don't know how I feel about that. What I would consider an objectively incorrect statement. Decorators aren't Python decorators. It's a pattern, you see? And specifically, this pattern is an object-oriented programming pattern, right? To say that it doesn't have it or that you can't use them in certain languages is just kind of incorrect. Because again, a decorator is not the syntax. Okay. Regardless, the question asks, function decorators are not as oft supported as plain higher order functions. True. We know it's true. Arguably true. Function currying, higher order functions, and first class functions are blank. Are they unique to purely functional languages? Are they unique to Python? Are they unique to OOP languages? Or are they commonplace in most programming languages? What do you think? Is it unique to purely functional languages? Is it unique to Python? Are they, I should say, function currying, higher order functions, and first class functions, are they unique to purely functional languages? Are they unique to Python? We know they're not unique to purely functional languages because Python is not a purely functional language. And we just got done talking about how other languages are doing this. We know we're in a functional programming course, so I'm going to, say we can probably run it out of this. We're not unique to OOP languages. So we're going to go ahead and say it is commonplace in most programming languages. They are commonplace in most programming languages. Alrighty, that is chapter 8 done. Some types. Remember when I said pure functions are my favorite part of functional programming? Well, some types are a close second. Some types are my favorite part of functional programming. A sum type is the opposite of a product type. Oh, just not exactly the right thing to say, but that's okay. This Python object is an example of a product type. We have a man that studies finance equals true, and we have a man that has trust fund equals false. The total number of combinations a man can have is 4, the product of 2 times 2. The total number of combinations a man can have, is 4, the product of 2 times 2. So he studies finance and he has a trust fund. Those are the only 2 properties. And so we can have true, true, false, false, true, or false, false. Any combination of those things. If we added a third attribute, perhaps a has blue eyes Boolean, the total number of possibilities multiplies again to 8. And so on and so forth. But let's pretend that we live in a world where there are really only 3 types of people that our program cares about. Are they dateable? Are they undateable? Or are they maybe dateable? There's only one guy. Let's be real. It's undateable. All right, so we can reduce the number of cases our code needs to handle by using a admittedly fake Pythonic sum type. I love that. He knew I was getting, like, Lane knows I'm coming for him on this. He's like, admittedly fake Pythonic. Okay, sum type with only 3 possible types. Okay, we have a person. They can be, we have a class dateable that takes person, class may be dateable, and a class undateable. They all take a person. They all have a name, so we can match on these things to check if they're an instance of one of those classes. Right. Then we can use this. We can use the is instance built-in function to check if a person is an instance of one of the subclasses. It's a clunky way to represent the sum types, but hey, it's Python. All right. And so we have here our example. I'll bring this over a little bit so we can see the whole thing. We have respond to text function, and we have a guy at the bar. And if the guy at the bar is a dateable instance of dateable, then we can get his name. And if he's guy at the bar may be dateable, we return something else. And then if he's undateable, finally, we say, have you tried being rich? Jesus, Lane. Or else, if it's none of these things, we can raise a value error, an invalid person type. And then we have sum types. As opposed to product types, which can have many, often infinite combinations, sum types have a fixed number of possible values. And to be clear, Python doesn't really support sum types. We have to use a workaround and invent our own little system and enforce it ourselves. Again, this is not entirely true because we have pattern matching in Python, and it depends on what you consider Python, where its limits are. Not entirely true. And if you use type checking, you can get like exhaustive matching and things like that, but not really in the scope here. That's fine. So for this assignment, whenever a document is parsed by doc to doc, it can either succeed or fail. In functional programming, we often represent errors as data. For example, the parse error class, rather than by raising exceptions. Because exceptions are side effects. In functional programming, we try to avoid side effects, right? There's also the reason a big reason is because you know what you're getting. If you're just raising exceptions or throwing, and there's nothing that says this function might raise an exception, right? It just does. And so you have to try catch and try to be safe everywhere because, well, you just have to assume everything can then raise an exception. Well, but if you know that you are going to get an error value back, then you can you can check if you have an error or a value or the value you wanted and handle it appropriately. And that is errors as values is, you have to take anything from me. It's just, that is so big. I love errors as values over just throwing things and then trying to catch them whenever, because you're going to forget one. Let's be real. But this way, in a statically typed language, it'll show you things like, oh, you have an error or a value. It means you forgot to handle the error case, and it forces you to handle errors. So this assignment, we're going to complete the parsed and parse error subclasses. The parsed represents success. It should accept a doc name string and a text string and save them as properties of the same name. Okay? And parse error represents failure. It should accept a doc name string and an error string and save them as properties of the same name. The test suite uses his instance to see if an error occurred based on the class type. Alrighty, let's see what we got here. It accepts a doc name and text and saves them as properties of the same name. So if the doc name equals doc name, or is it not? Do I even have to do that? Do I just save it like this? Just so out of practice with Python. No, so I gotta go self that. Sometimes moving between languages a lot has drawbacks. All right, so then parse error represents failures. It should accept a doc name. It's the same thing, right? Same but different. Alrighty. Oh, so put me over here. We'll run this. No error, no failures. Good to go. Submit. Bling. And we are moving on.
Enums are one of the best things to happen to programming, and that's including the release of the best operating system of all time, Windows Vista. But before we talk about enums, let's brush up on a little bit of category theory. And despite the word theory being added to scare non-academics, it's really not too bad. In programming, types are how we categorize things. For example, this partner class contains two variables, both of which are Boolean types. So the partner type actually contains other types. And this is common when working with collection types like lists, tuples, and classes. The interesting thing about this partner class is that it really has four possible combinations of values. Studies finance can be true, has trust fund also true. Studies finance true, has trust fund false. Studies finance false, has trust fund true. Studies finance false, has trust fund false. And that seems manageable, but what happens if we add a third field? Well, if it's also a Boolean, then the number of possibilities actually jumps up to 8 because we have to multiply 4 by the available combinations again, which is 2, getting 8 possible total combinations. If we add another, we get 16, and if we go up to 5, then we get a total number of 32 combinations. And if we add a string into the mix instead of a Boolean, then the number of total possible values essentially goes up to infinity because a string can contain any number of combinations of characters. Now, this is where the term product type and sum type come into play. And they're also sometimes referred to as algebraic data types just to scare the non-PhDs. The partner class is a product type because the total number of possible combinations of values is the product of the number of fields, right? 2 times 2 times 2 times 2 times 2, however many Boolean fields we had in there. But product types are very interesting. Almost everything is a product type by default. Lists, tuples, and classes with, a number of properties. And the problem is that product types result in many possibilities. And even primitive types like strings and integers have the same problem. When you have a string type, you don't know if that string value contains the entire text of the novel Moby Dick, or the string Hello World, or the empty string. There's so many possible combinations that could be stored in that type. And that makes them hard to work with. Right? When you write a function that accepts one of those types as a parameter, you have endless if-else statements and switch cases and fallbacks to handle all of the different possibilities that could arise when your function is called with different values. That's where sum types come into play. They're just types where the number of possibilities is limited to a finite set. A Boolean is a good example of a sum type. It has two possibilities, true and false. When you're working with a Boolean, all you have to think about is whether this variable is true or false. Okay, so now we can finally talk about enums. Enums are another sum type, like a Boolean, and really I like to think about them as kind of extended Booleans. For example, let's say we want to write a button class, and in this button class, we want to specify that it can be one of 3 colors. We could have the buttons constructor accept just a string to define which color it's going to be. And we'd accept either the string red, the string green, or the string blue. Now, the problem is that our button class now needs to take into account that whoever's creating a new button could pass in any string, right? They could pass in the string teal, or they could just pass in a misspelled blue, and we need to handle both of those cases. The better option is to use an enum. And at least in Python, the way you can define an enum is using the enum package. You pass in the name of the enum, in our case, we'll use color, and then the possible values that are valid in this new type. So in our case, red, green, and blue. Now in our code, if we use color.red, it will work. It will resolve to the color red. And as far as the color type is concerned, everything will work smoothly. But if we try to use a color that was not specified when we created the color type, like teal, the Python interpreter itself will actually throw an error. So now the language itself will raise an exception if we ever try to use the wrong value. And that means that in all of our code, we no longer need to have all of these if-else statements checking and making sure that the variable maps to a valid value, right? There might be 10 different places in code that have to check the value, and we don't want to rewrite all that code. In a language like Python, the interpreter will yell at us when we run the code if we ever use an invalid value in an enum type. But in statically typed languages, like a lot of the compiled languages like Go or TypeScript or C, we'd actually get the errors either at compile time or even better, right in our editor telling us that those values are not allowed for that type. That said, enums are still useful even in a language like Python. Python's not statically typed, so it does mean we'll have to actually run the code to see the type errors, but at least the valid values, red, green, and blue, are defined when we create the enum type. So there's a single place to reference, so we as developers can see what colors are valid types, and we won't have to keep redefining it every time we check the value.
Enums. Doing the admittedly weird class and is instance thing works, but it turns out there's a better way in some cases. If you're trying to represent a fixed set of values but not store additional data with them, enums are the way to go. Let's say we have a color variable that we want to restrict to only 3 possible values, red, green, or blue. We could use a plain old string to represent these values, but that's annoying because we have to remember all the valid values and defensively check for invalid ones all over our code base. Instead, we can use an enum. So we have from enum import enum, and we can go color equals enum color, red, green, blue. I think there's also another way to do that too that we might look at here. Now, color is a sum type, at least as close as we can get in Python. There are a few benefits. A color can only be red, green, or blue. If you try to use color.teal, Python will raise an exception. There's now a central place to see the valid values for color, and each color has a name, right? So color.red is the name and a value, for example, 1. The value is an integer and is used under the hood instead of the name. Integers take up less memory than strings, which helps with performance. And if you don't need an associated value, perfect, just fine. So for this assignment, we're going to create an enum called doctype with the values PDF, text, docx, MD, and HTML. So we're going to from enum import the enum class, and then what we can actually do is we can say class doctype. This can be enum, right? That I'm thinking. So I think I can go auto here, and then I can go PDF equals auto, txt equals auto, and I think we can manually do 1, 2, 3, 4, 5, whatever. Docx equals auto, MD equals auto, and HTML equals auto. Let's see how if this actually works. Boom, 4 passed, 0 failed. Boom, call it good. So the way, and then just for completion's sake, we'll go ahead and comment that out, and we'll say doctype equals enum, and you can also do doctype. See, this is a little more verbose, right? And then so we make a array or a list of PDF, txt, docx, and MD, and HTML. And then same thing, submit, still good to go. Same thing, same thing. That's that. Now on to the next one. Sum types. Unfortunately, Python does not support sum types as well as some of the other statically typed languages. Python does not enforce your types before your code runs. That's why we need this line here to raise an exception if a color is invalid. In a language like Rust, we could write the same thing like this. Boom. Notice how there isn't any case for an unknown value. That's because the Rust code will fail to compile, a step that happens before the code runs at all, if the color is a different value. This static enforcement is a huge benefit of sum types, and it's a shame we can't get that in Python. Let's go Lane. Which language does not support proper sum types? Is it Rust or is it Python? Let's go. It's Python. We're almost done, nearing the end of our time together learning about functional programming. For today, we'll talk about that in a little bit. Continuing on, why are sum types useful? You have to run your code to see if you've handled all possible cases. You can know before you run your code that you've handled all possible cases, or they ensure that your variables can hold any type of value. And that's going to be the reason that they're so good normally, not necessarily in Python, is because you can know before your code even runs that you've handled all possible cases. You can't just have any string or any value. You're constrained to one of these 3. So that one. Moving on. Let's take another look at our example enum from the previous lesson. Working with enums. Python has a match statement that tends to be a lot cleaner than a series of if, else, elif statements when we're working with a fixed set of possible values, like a sum type or more specifically an enum. If we have get hex, we can have match color, and we can go, over the cases and return. And then we have a default case because We don't actually need that in this case, but the type checking isn't on. So if you have two values to match, you can use a tuple. You can say get hex, you can say color shade, and you can match on the tuple. And you can have two different enums and like match each one of those, each possible option, and for each one. So for the assignment, we can complete the convert format function. It should support three type of conversions. It should support from MD to HTML. We're going to assume the content is a single H1 tag and Markdown syntax. It's a single string representing a line. Replace the leading hashtag space with the H1 and add an H1 to the end. Easy enough, right? And then, so from text to PDF, we're going to add a PDF in brackets tag to the beginning and end of the content. Notice the space between the PDF tags and the content. Yep, so we got a space there. Right on. And then from HTML to MD, we're going to replace any H1 tags with the Markdown syntax, the hashtag space, and remove any closing H1 tags. For any other conversion, we're going to raise an exception with the string invalid type. Got it. We're going to be matching the from format and the to format. And then we're going to say the case, if the case is docformat.md and to docformat.html, then we're going to assume the content is a single H1 tag in the Markdown syntax. And we're going to replace the leading. So we need to say no leading equals where we can go content. Is it content.lstrip? And then we're going to do that. We can return an F string where we do H1 and then the closing H1, and then we can go no leading. And then we have our case of docformat.text to docformat.pdf. And all we're doing here, we're just adding the PDF tag. So just an F string with the content, PDF with the space after, and PDF with a space before. And then we have case HTML to MD and docformat.md. And then in this case, call it stripped equals content.lstrip, strip any leading H1s and rstrip any trailing closing H1s, right? And then we're going to return an F string with that, and then stripped. And then for the last one, we do a case underscore, and we raise exception of invalid type, just like that. That said, we can try to run this and see if we got it right. First try, no big deal. Let's see if we submit it and if we're good. And if so, we will have completed this course. Let's see. Woo! We did it. We did it. We went through the Boot Dev Learn Functional Programming course, and I only embarrassed myself a few times. Look, course complete. I got the pupil role. And we just completed the Learn Functional Programming course in Python.